Welcome to the lecture number 6. If you recall, on the last lecture we had estimated the parameters beta 0 and beta 1. We had further investigated their statistical properties. We had proved that beta 0 hat and beta 1 hat are the unbiased estimators of their respective parameters, and we also found their variances. In the model, there were 3 parameters: beta 0, beta 1 and sigma square. Out of those 3 parameters, we have estimated 2 parameters, but the third parameter is still left. So, we start with the estimation of third parameter, which is sigma square. There is a difference in estimating sigma square and the 2 parameters beta 0 and beta 1 by using the principle of least squares. There is no involvement of sigma square in the function s beta 0 beta 1 that we had defined earlier. So, it is not possible to differentiate s with respect to sigma square, put it equal to 0 and solve the equation to get the value of sigma square. So, in order to obtain the least square estimate of sigma square, we start with some estimator based on our guess. Now, the next question is, how are we going to make a guess? We had discussed that residuals are the difference between observed and fitted values, and sigma square is the variance of epsilon i's. So, one option is that I can consider a quantity like summation I goes from 1 to n epsilon I hat square, and then we try to take its expectation. This will come out to be as a function of sigma square. Then we adjust it to obtain a good estimator of sigma square. So, before doing that, let me define it. So, we try to define something called residual sum of squares, and that is defined as sum of squares of the residual, right. So, call it as SS res. SS res means sum of square due to residual. RES means it is a short form of residual. But before going further, let us try to understand it. This quantity has some important role in the regression analysis. So, we would like to solve it further, and let us try to obtain different possible forms of sum of square due to residuals. So, right, if you try to see here, this quantity is nothing but I goes from 1 to n, say here y I minus beta 0 hat minus beta 1 hat x I whole square, right. So, I can now make it like this. I try to substitute the value of beta 0 hat, which is equal to y bar minus beta 1 hat x bar, and then this becomes y I minus y bar minus beta 1 hat x I minus x bar whole square. And this can be further written as summation I goes from 1 to n y I minus y bar whole square plus beta 1 hat square summation I goes from 1 to n x I minus x bar whole square minus twice of beta 1 hat summation I goes from 1 to n x I minus x bar y I minus y bar. If you recall earlier, we had defined the quantity like Sxy. This Sxy was defined here as a summation of I goes from 1 to n xi minus x bar yi minus y bar. right. So, on the same lines I can define SYY as a I goes from 1 to n yi minus y bar whole square. So, this quantity now becomes SYY plus beta 1 hat square, and this quantity is nothing but your SXX minus twice of beta 1 hat SXY, right. And we had seen that beta 0 hat is this and beta 1 hat is SXY over SXX. So, I can write down this SXY as a beta 1 hat times SXX. So, this becomes here SYY plus beta 1 hat square SXX minus twice of beta 1 hat square SXX. So, this can be written as SYY minus beta 1 hat square SXX, right. This is one possible form. Now, I can replace here the value beta 1 hat is equal to SXY upon SXX, and this I can further solve as SYY minus SXY over SXX whole square SXX, and this will come out to be SYY minus beta 1 hat SXY. So, this residual sum of squares has got several popular forms, and depending on the need and situation we try to use them suitably, right. Okay. Now, our next question is how to obtain the estimate of sigma square. So, let us try to use sum of square due to residual to find out a estimate of sigma square. But before that we need to find out the distribution of yi. So, since we assume that our model is beta 0 yi is equal to beta 0 plus beta 1 xi plus epsilon I, and we have assumed that epsilons I are following a normal 0 sigma square distribution and they are IIDs. So, I can write down here that expected value of yi is nothing but beta 0 plus beta 1 xi, and we also have found earlier that variance of yi is equal to sigma square, right. And moreover, yi's are the linear combination of normal random variable of normal or normally distributed random variable, which in our case is epsilon. So, I can also write that yi will also be a normally distributed random variable. Right. So, I can write down here yi's are going to follow a normal distribution with mean beta 0 plus beta 1 xi and variance sigma square, right. Now, are they also IID? If you try to see, they are independent, but they are not identically distributed. Why? Because the distribution of yi is depending on xi. So, as the observation changes, the mean of the normal distribution also changes. So, yi's are independently distributed following a normal distribution with mean beta 0 plus beta 1 xi and variance sigma square, right. So, once I can write this thing, then we also know that sum of squares of normal random variable follows a chi-square distribution. So, if there are n random variables, each of them is following a normal random variable, then their sum of squares will follow a chi-square distribution with n degrees of freedom. So, in case if I try to use this thing, this sum of squares due to residual, if you try to see, this is nothing but the sum of squares of normal random variables. So, I can write down here that SS residual divided by sigma square, this will follow a chi-square with n minus 2 degrees of freedom. One question comes, how does it 2 comes into picture? Since I know that epsilon I hats, they are depending on 2 unknown parameters beta 0 and beta 1, which we are estimating as beta 0 hat and beta 1 hat. So, there are 2 unknown parameters which are being estimated in finding out the epsilon I hat square. So, that is why there are 2 constraints, and so the degrees of freedom are reduced by 2, and the degrees of freedom of this chi-square random variable are n minus 2. Right. So, just for the sake of your information and a quick review, means we know that if there is some random variable z which is following a chi-square distribution with n degrees of freedom, then its mean is, that is, the expected value of z is n, that is the number of degrees of freedom, and variance of z, it is nothing but twice of n, that is the twice of the number of degrees of freedom. So, if I try to find out here the mean of this quantity, so I can write down here expected value of SS res divided by sigma square. This is following a chi-square distribution with n minus 2 degrees of freedom. So, its mean is going to be n minus 2. And so, I can write down here, or I can write down here expected value of SS res divided by n minus 2 is equal to sigma square. So, this implies that sigma square hat is equal to SS res divided by n minus 2. So, this is an unbiased estimator of sigma square. Right. So, now if you try to observe what we have done, we started with the model yi is equal to beta 0 plus beta 1 xi plus epsilon I, and based on that we have 3 parameters beta 0, beta 1 and sigma square. All of them were unknown to us. What we did? We collected a sample of data and we had n observation, something like x1, y1, x2, y2, xn, yn. Based on that, we have obtained the estimate of beta 0, estimate of beta 1, and now we have also obtained the estimate of sigma square. So, now these 3 parameters can be estimated using these 3 estimators. So, now we can say that my model is known to us. There is now another question. When we are trying to estimate my model parameters, for example, we have estimated beta 0 by beta 0 hat and beta 1 by beta 1 hat, how I can say that these are good or bad? We have established that they are unbiased estimator, and we also have found their variances, and we had obtained their variances like this. Variance of beta 1 hat, this was observed as sigma square upon Sxx, and variance of beta 0 hat was observed as sigma square 1 over n plus x bar square over Sxx. Right. Once we are trying to estimate the parameters on the basis of a sample, I would also like to know what is the variability of my estimators, because there can be more than one estimator for the same parameters that can be unbiased. But then how to choose among them? I will try to choose the estimator which has got a smaller variance. So, now I have got these two variances, but these are the values of the variance in the entire population. If you try to see here, this is depending on sigma square. here and C here, and sigma square is the value in the population. So, these two variances are going to be unknown to us. So, my next objective is how do I estimate the standard errors of beta 1 hat and beta 0 hat. Right. So, one option is that now since we have obtained that sigma square hat is SS res divided by n minus 2. So, one option is that I can write down the variance of beta 1 hat as say sigma square upon SXX, but in this case I do not know this variance. So, I can do one thing, that I can replace sigma square by sigma square hat. So, I am trying to replace sigma square by sigma square hat, and so now this gives me an estimator of variance of beta hat. So, now this is estimator of variance of beta 1 hat. Now, what is the advantage? That once I get a set of data, I can estimate my model parameter beta 1 using the ordinary least square estimator SXY upon SXX, and now I can also provide its standard error just by taking the positive square root of estimate of variance of beta 1 hat. So, this will also give us an idea that what is the performance of my estimator in terms of the variability. Right. Similarly, I can also find out the estimate of the variance of beta 0 hat. What I have to do? I simply have to write down the variance of beta 0 hat, and I have to replace sigma square by sigma square hat. And if I want to find out its standard error, it is very simple. Just try to take the positive square root of estimate of variance of beta 0 hat. That is all. So, now I have got both the estimators beta 0 hat, beta 1 hat. I have shown that they are unbiased, and I also have found their standard errors. So, once I try to write down a model, give its parameter, find out the estimate of all the parameters as well as standard errors, up to certain extent we have obtained a model. Right. After this thing, there are some other considerations like test of hypothesis, confidence interval estimation on the estimated parameters. So, that we will try to continue with those things, but before that let me try to explain you one more thing. We have considered here the simple linear regression model yi is equal to beta 0 plus beta 1 xi plus epsilon I. Right. This is a model which has got intercept term. Now, there can be another situation where we need to consider a model without an intercept term. Right. So, in that case what would happen? That I would try to consider the model something like yi is equal to beta 1 xi plus epsilon I. The first question comes, what is the difference between the two? Why should I consider the intercept term sometime to be present or sometime to be absent? I will try to take a simple example and I will try to explain you. For example, when I consider an example of yield of a crop. So, for example, yield of a crop depends on the quantity of fertilizer and say rainfall, temperature and so on. In this case, if we try to put some fertilizer in the soil, means our crop will increase. But on the other hand, if we do not put any fertilizer, the soil itself has some inherent fertility, and because of which I will get some yield. right. So, if you try to see here what is the interpretation of here yi, if you try to if I try to write down here the model in terms of expectation, if I have the intercept term in the model, this model is like this with intercept term, and this model is something like beta 1 xi if I do not have the intercept term. So, if you try to see what is the interpretation of beta 0, beta 0 is nothing, but if I say if xi is equal to 0, then expected value of yi is equal to beta 0. So, that means beta 0 is nothing but the average value of y. So, now in this case, when I am trying to put 0 fertilizer in the soil, am I getting 0 outcome? On the other hand, if I try to take the model without intercept term, that is something like beta 1 xi without intercept term, then if xi is equal to 0, then expected value of yi is equal to 0, right. So, if I try to take an example to explain the two situations, I can say in the case of crop, when I put no fertilizer in the soil, still I get something. So, my outcome is not 0. So, the average yield is not going to be 0. So, in that case, I would like to have a model with an intercept term. On the other hand, if I say that y is my here something like the luminance of a bulb, and xi is my say current. We all know that when we switch on the switch, then some current goes into the bulb and then the bulb glows. But if I put no current inside the bulb will not glow and the luminance will be 0. So, in this case, I know when I put xi is equal to 0, then my average value of yi is always 0. So, in this case, I would like to have a model without an intercept term. So, there are situations in practice where sometimes I have to consider a model with intercept term and sometimes without intercept term, and based on that I would like to show you in this simple framework that what happens to the estimate of parameters, right. So, now in case if I try to consider here a model yi is equal to beta 1 xi plus epsilon I, all my assumptions remains the same as earlier, right, that beta 1 is a parameter, xi is my fixed, it is non-stochastic, and epsilon i's are my IID normal 0 sigma square random errors, right. In this case, my objective is to find out the parameter value beta 1. So, I again use the principle of least square and I try to minimize the sum of squares, which I try to denote now here S of beta 1 I goes from 1 to n epsilon I square, and this is nothing but your I goes from 1 to n yi minus beta 1 xi whole square. Now, when I try to differentiate it with respect to beta 1 and put it equal to 0, this gives me minus twice of summation I goes from 1 to n yi minus beta 1 xi, say xi is equal to 0. And when I try to solve it, this gives me the value of here beta 1 as say summation I goes from 1 to n xi yi upon I goes from 1 to n xi square, right. So, this is an estimator of beta 1. So, I can denote it as a say beta 1 say star hat. I am trying to use here a to notation star just to distinguish beta 1 hat from the beta 1 hat that was obtained in a model with intercept term. Right. So, because for the sake of clarity, I can write down here that your here beta 1 hat is Sxy upon Sxx, which was summation xi minus x bar yi minus y bar upon summation xi minus x bar whole square. Right, and this was obtained in the model yi is equal to beta 0 plus beta 1 xi plus epsilon I. Right, so that there is no confusion between the two symbols of the beta 1 hat. So now, what do you observe here? Does this expression and this expression are the same? Not really, they are pretty different. So, the moral of the story is that when you are trying to fit a model with intercept term and model without intercept term, there is one parameter, that is the slope parameter beta 1, that this is common, but their estimators in the two models, they are different. That you have to keep in mind. Now, it is also not difficult to show that the second order derivative of beta 1 with respect to beta 1 square at beta equal to beta 1 hat star, this comes out to be greater than 0. So, this implies that beta 1 hat star minimizes S beta 1. So, now this beta 1 star is the ordinary least square estimator of beta 1 when we have no intercept come in the model. So, now at the same time we can do a similar exercise and we try to establish the statistical properties, that is finding out the unbiasedness character and the variance of beta 1 star. So, beta 1 hat star here is now here summation I goes from 1 to n xi yi upon summation I goes from 1 to n xi square. Right. So, I can find out expected value of beta 1 hat star. This comes out to be summation I goes from 1 to n, say xi expected value of say here yi upon summation I goes from 1 to n xi square, and this quantity is nothing but I goes from 1 to n, say here say xi, and expected value of yi is nothing but beta 1 xi upon summation I goes from 1 to n xi square. So, this quantity is nothing but summation I goes from 1 to n xi square upon summation I goes from 1 to n xi square, and this is same as beta. So, this remains unbiased estimator. So, beta 1 hat star is an unbiased estimator of beta 1, that is established. So, there is no change in the property of unbiasedness of the slope parameter of the two estimators in the case of model with intercept term and model without intercept term. Right. Similarly, if I try to find out here the variance of here beta 1 hat star, this is nothing but summation I goes from 1 to n xi square variance of here yi divided by summation I goes from here 1 to n xi square plus whole square, and the cross product terms becomes equal to 0 because we have assumed that y1, y2, yn are independent, and we already have established that variance of yi is sigma square. So, once I substitute this thing, this comes out to be nothing but sigma square I goes from 1 to n summation xi square. Right. And in this case, if you also want to find out the estimate of sigma square, that can be also obtained quite easily. Sigma square hell, let us try to say star. So, this can be obtained here as say 1 upon n minus 1 summation I goes from 1 to n yi square minus beta 1 hat say star summation I goes from 1 to n xi yi. So, you can see here that even the estimator of sigma square in case of model without intercept term is quite different than the form of the estimator of sigma square when there is an intercept term in the model. So, the moral of the story is that that if you do not want to consider the intercept term in the model, please don't do like this, that you fit a model with intercept term and you simply substitute the intercept term equal to 0 and use the same estimates. You will need to find out the estimates of the parameters separately, and the standard errors of the parameter estimates will also change. So, we stop here in this lecture, and in the next lecture we will try to consider the maximum likelihood estimation of the parameters beta 0, beta 1 and sigma square, and we will try to see how does it make a difference when we try to use different estimation techniques to estimate the parameter. Thank you, and till then, goodbye.